Today is Friday, February 9th. This is Season 2, Episode 6 of Mind, Body, Evolution. Hi, Josh.
Hi, Eric. I was thinking today of getting a little bit away from the philosophical, mystical side of things that we've been traveling for a while, and gender speculation and all that, and getting more towards the direct discussing of evolutionary health. And I wanted to
like that idea.
Yeah, I wanted to talk about sugar because it's right at the center of evolutionary health and who we are as a strange kind of animal, and how we interact with the world.
It's also very interesting because when we were growing up, you and I, the great evil was fat.
Yes,
but now the great evil is
clearly sugar. It's clearly sugar. The great evil was fat because we didn't want to get fat. But sugar is more like money. And everyone wants money, but money is the root of all evil. And it's because of the desire. And the desire is built in. And money is a pale comparison to the desires related to sugar. Money is just feeding into our symbolic understanding of what we want.
Did we ever encounter sugar when we came out of the trees onto the Serengeti?
Oh, before then. Before that. Sugar is everything for everyone. Sugar is the thing that cells use to make energy. It is the number one molecule that everyone wants. If you're a bacterium, if you're a protist, if you're an amoeba, everyone wants sugar. I knew people who were working with aquaculture, and when you first start a project, you need your filter to actually have things living in it so you can start denitrification processes. And so they wrote this great paper saying just add sugar. Because
just add sugar to water?
You have an aquaculture setup and you have to let it sit there and reach equilibrium for weeks at a time, or you can just dump a pound of sugar in there and boom. Everything is all set.
Everything's like, what?
Yeah, everyone loves sugar. And so this is right from the very beginning. Everything is motivated to get sugar. I think I mentioned this when we were talking about dopamine, but there's we only have 5 flavors, and 2 of them attract us: the savory and the sugary. So that sugary attractiveness is built in really from the beginning. There's only a few things that can cross the brain-blood barrier, and glucose is one of those things. Must be able to. Cannot be. Your brain only has really seconds worth of fuel without sugar going into it. You'll die in under a minute if the sugar isn't coming in at a really steady state. So we're very, very concerned about keeping it, and more than most other creatures. This is why I was saying that everything loves sugar, but we are evolved to have a different relationship with it than most other creatures because of our giant brains.
Because our brains are very, very hungry.
Very hungry all the time. We're like a furnace, and we just have to keep feeding them all the time. No other animal has a brain like ours and needs to feed it in the same way. Even the cetaceans, they have very large brains, larger than ours, but compared to their body mass, it's nowhere in our league. Ours is comparatively like 4 times larger than a whale's by body mass. So our brains are taking in a tremendous amounts of energy, and we've also been focused on sugar since the very beginning. We as primates, fruit was important in our diet, and so digesting sugars was something that was really important to us and was closely related to all the rewards we would see. So we would see a red color, and dopamine would be released, tell us to go get that sugar, and then we would eat the sugar. Sugar and dopamine together are some strange things. This is not really well understood by anyone, and because you can't give dopamine to things directly, but I did it. With my shrimp, and I can't even talk about it in a meaningful sense because I got the opposite reactions than anything I'd ever done. Dopamine is inhibitory in crayfish. Glutamate, the other flavor that also goes through a brain-blood barrier, tells you to run after things. Glucose also tells you to run after things like glutamate, just as I would expect. But you combine it with dopamine, glutamate, inhibition. Dopamine, glucose, more excited than before you started. Can't fit it into my model, can't fit it into anybody's model. Strange stuff. So there's an interaction directly between dopamine and glucose. Glucose causes endogenous dopamine to be released. But if you combine it with exogenous dopamine, you get all sorts of strange reactions. It might actually explain some of this stranger studies done on hyperactivity. Hyperactivity is understood as a low dopamine condition. Every parent in the world knows that if you feed sugar to your child, you have a hyper child. No study has found this. Over and over again, you feed sugar to a class of toddlers or kindergartners, and there's no measurable increase in activity by people who don't know if they've been given sugar or not. So there's no easy way to see what everyone knows is true in any way that can be measured.
How could that be possible?
I don't know. Some of it is the sugar companies like to sponsor studies that don't come up with good conclusions. You have a small study size.
Well, okay, if you're going to say it's funded by Domino, okay.
A lot of stuff gets funded by Pepsi and Coke. So anyway,
what good is that?
Okay, so we've moved past that, and we still do studies, and they still don't show any hyperactivity related to sugar. However, when you start thinking about it as a dopamine-sugar interaction, there might be special effects that affect particularly ADHD kids more. When you have a dopamine issue, there might be effects of sugar that relate differently. I don't know the answer to this. No one knows the answer to this, but I think there's
and we haven't specifically studied this. I mean,
not really.
You'd think we would want to.
Well, it's not easy to. We've definitely studied dopamine and sugar and dopamine on its own and drugs with dopamine, but you can't get dopamine and sugar into a rat easily on its own, just as like a, here, have this dopamine food.
You mean
you have to give them cocaine?
You mean we're not going to study directly on children?
And we can't. It's not easy to study directly on children, but what we do is you feed sugar directly to a rat and you can see activity signs, but those activity signs go down quickly. And I saw the same thing in my crayfish. You give sugar to a crayfish and activity goes down over time, probably because of something along like insulin. But don't give insulin to a crayfish. I tried that. It turns out to be the equivalent of testosterone for a crayfish. It turns them into males. And gives you even more confusing answers. So the whole thing is weird. Okay, so stepping back again.
Yeah, okay.
Yeah, stepping back to the beginning of us being primates. We really like fruit. We're very attracted to this. There's rewards associated with it. There's dopamine associated with it. So we're very attracted to seeking sugar, as is every other living creature. Everyone wants the glucose to feed their metabolism. When we start moving out into the Serengeti and we leave the fruit trees in the jungle behind, we become more dependent upon starchy sources of food. So instead of directly glucose and fructose in sweet fruit, it's tubers, and it's things that have sugars all linked together into these long molecules called starch. And we need enzymes to break those down. And so we start producing more copies of these enzymes that break down starch. These copies are maybe 2 in a chimpanzee. If you look at the few people who have stayed in rainforests for most of their evolutionary history, so, the last, say, 60, 70,000 years, they have maybe 4 or 5 copies of amylase, the enzyme that breaks starch, amylose starch into individual sugar units that you can digest. So humans, even the ones living in the rainforest, have more copies of it. The Hadza, the hunter-gatherers of South Africa, have 6 or 8 copies. So even if you're not a farmer, you have more copies of amylase than a chimpanzee does. And farmers have anywhere from 8 to 14 copies. So the more copies of a gene you have, the more you can make that particular enzyme, and so the faster you break down the sugar. So our entire evolutionary history since we became bipeds has been dedicated to getting sugar out of starch faster. And when you get sugar out of starch quickly, your blood sugar goes up for obvious reasons. You have sugar in your blood. And so we were very, very dedicated to that. At the same time, we are having a hard time getting enough calories. We've got these large brains. We've become bipeds. We're not very large-brained at this point, but there's not a lot of food out of the Serengeti. We're going around digging up roots. and chewing on roots all day. So we've emphasized efficiency. We became bipeds because it was an efficient way to get somewhere, not a fast way, but very efficient. So we're doing the same thing with our metabolism. We're slowing down our metabolism. Rather than speed and strength, we're emphasizing taking all that sugar and storing it as well as we possibly can. So we change all of that starch into sugar that we can absorb as quickly as we possibly can. We even do it in our mouth before we swallow. So we're breaking down starches in our mouth. They'll taste sweet. If you have a cracker in your mouth for long enough, it'll start to taste sweet. That's the amylase in your saliva breaking it down. You swallow it, even more gets broken down. You're absorbing every bit of that starch you possibly can. And it's because we were sort of the poor relations of the chimpanzees. We didn't have the nice sugary fruits. We had to get everything out of really hard to digest items, and we had to get every little bit of it. And when we get that sugar, we store it right away. So what happens is blood sugar goes up and you respond with insulin. Insulin does a couple of things. The nice thing insulin does is it helps put sugar into your muscles. So you'll feel a little bit stronger because you've got a little bit of
get a little jolt.
At the same time, it's going to be sending sugar to your liver where it gets stored as glycogen. So insulin tells that sugar to become part of this gigantic molecule. It's weird. It looks like a spider web of sugar molecules. The world of liquid physics is weird, and it doesn't matter the size of a molecule. It all has the same osmotic pressure. And so if you want to raise the osmotic pressure, you could say add more salt. You want to lower it, you take less salt. But if you took all of that salt and put it into one molecule, it would only count as one molecule, no matter how big it is. So the same thing with sugar. We take all of that sugar and we pack it into a single molecule of, say, 50,000 glucose molecules in one glycogen molecule. And that gets stored in the liver. And that's our temporary energy supplies. And so insulin causes the sugar that we extract every little bit of from our food to get stored.
We literally store it in a nugget in our livers.
Yeah, lots of little nuggets.
Lots of little nuggets all throughout our liver.
Right, and if it was stored as sugar directly, we would explode because there would be so many molecules in there that our liver would have all of the water in our body being sucked in. But by turning them into many fewer molecules, by packing them together, we can maintain balance between the liver and the rest of our body. It's super important to do this. This is where all of your temporary energy is going to be coming from. So these molecules can be quickly released. So if you need energy, you have the other side of the equation is glucagon. Glucagon is the hormone that then tells the glycogen to release that sugar into your bloodstream. So when your blood sugar goes low, glucagon is released and you release the sugar. When your blood sugar is high, insulin is released and you store it as glycogen. But insulin itself is actually an anabolic steroid. It is related to the other anabolic steroids, progesterone, testosterone, human growth hormone, all of those anabolic steroids. And what it does, in addition to signaling, let's store the sugar, is it says make fat. And so it takes sugar out of your blood system and turns it into fat. And different parts of your body respond to hormones differently, particularly the kinds of fat in your body. So you have subcutaneous fat that is lying just under your skin, and then you have visceral fat that lines your organs and tends to be what we call belly fat. Belly fat responds more strongly to hormones than do other kinds of fat. So you preferentially send this extra sugar to your belly. And so the more sugar...
men do.
No, everyone does.
Everyone does. Okay.
Oh, yeah. No. Evolution is very sexist and makes things harder on women. Women have a higher total fat content and have a body that's going to be emphasizing storing fat more extremely even than men. We are pushing the envelope for storing fat among the animal kingdom, but women surpass us in the ability to store fat because you're not fertile if you don't have fat. And the reason you're not fertile is we have these giant brains. Again, it's all about feeding these giant brains a constant supply of glucose. Even a minute without sugar and you're dead. It really happens very, very quickly. halfway to that minute, it's going to be very difficult to eat, for example, as you're passing out. So you only really have a few seconds.
Oh my God.
So your insulin levels are controlling your blood sugar, but so is glucagon controlling blood sugar. And between the two of them, they're releasing it mostly from the liver. But once you run out of glycogen in your liver, when you run out of those temporary supplies, you only have maybe 4 to 6 hours of that. Then you can actually start burning fat again. And the fat will actually be released again, preferentially from the visceral fat. So it's like first hired, first fired. It's the fat that gets stored first is the first that comes out. And so this is why
most accessible. It's
most accessible. And so this is why some people like the idea of what they call the paleo diet or low carbohydrate diets. A low carbohydrate diet is designed to lower your blood sugar and start removing it from your liver. And that way you can then start burning fat. And this will work. If you do this, you will start burning fat, but you'll also start burning muscle, and it can be really bad for you metabolically. You can go into acidosis, ketosis. These things can cause various kinds of metabolic issues.
I know somebody who's on it for a long time and started losing their hair.
It can also radically increase your what they call bad cholesterol. We'll have a whole nother thing on cholesterol. I don't really believe in just a good and a bad form, but let's just for now we'll say the low density lipoproteins. It will increase those and your total triglycerides. So you could.
That sounds bad from the little I understand.
Exactly, that's bad. So you can end up with high blood pressure and clogged arteries and arteriosclerosis due to something that is burning fat successfully. That part really does work.
But again, what you're saying is that the whole of our evolution has brought us to a point now where all we want to do is eat sugary things and sit there and store them up as fat, sit on the sofa and be happy.
You got it. Yes. No, that is everything that we are designed to do. We should not exercise and we should eat as much sugar as possible. Evolution does not care about your health. It just wants you to produce big brain babies that produce more big brain babies. That's all it wants you to do.
And then you can die.
Yeah.
As long as they're on their way to making more babies.
As long as they're on their way and maybe a few women make it to 50 to lead the group. That's what evolution really wants.
It's not on our side.
It's not on our side. If they make it to 50, they've been through menopause, they're not doing the baby thing anymore, and now they're leading the group, and it's inclusive fitness for everyone. But as men and women, the evolution basically wants us to get as fat as possible and spend all of our time being fat and making babies. It doesn't care about doing any other activities. So if you are on a paleo diet, you can reduce your glycogen stores and start burning fat, which will work, but as we just talked about, is not necessarily great for your health. But there's other ways to do it. This is why I talked about intermittent fasting. Intermittent fasting can do the same thing, but is working with evolution. We are designed.
I mean, you talked about ketosis. Intermittent fasting puts you into ketosis, which before you said was a dangerous situation.
So intermittent fasting does it for a very brief amount of time.
Yes.
It's hours of a day.
Correct.
You are well evolved to withstand that. It is not over weeks or months of time, like a steady paleo diet where you're trying to avoid.
That's when it becomes
any kind
dangerous.
of sugar. Yeah, because you're doing it all the time. We are well designed to stop eating for a while. A day, even 2 days, our body responds well. And we start doing things that are actually good for us. For example, we become more susceptible to the effects of insulin. Now you'd be like, well, I don't want insulin to make me fat, because insulin is the thing that does store fat. But susceptibility to insulin is really, really important. The opposite of susceptibility to insulin is type 2 diabetes, is when you lose your body's response to insulin. What happens if your blood sugar goes up and you don't start taking that sugar away by making it into glycogen, you then have high circulating insulin and high circulating blood sugar. This is going to cause any sugar your body can find to be turned into fat, because that insulin is a anabolic steroid.
Insulin sensitivity means your body's awareness that there is insulin in your body and you should be signaled to stop eating sugar.
You'll immediately feel full. and you'll take any sugar you have and you'll deal with it in the liver. You'll turn it into glycogen. It'll store it away.
And a low insulin sensitivity is, even though the insulin is there, I'm not being told to stop eating.
You're not being told to stop eating, and the insulin is telling you to turn everything into fat. So you'll become fatter more quickly. And preferentially, that fat will start being made in the liver. And when you start turning your liver into fat, you don't have as much of a liver with which to process things anymore. And the only thing your liver can do with that unprocessed sugar is to turn more of it into fat. And you start converting your entire liver into a big blob of fat that can't do any processing anymore. And this is the heart of metabolic disease, because you get into a feedback loop where you're responding less and less to the insulin, your blood sugar is going higher and higher, and you're destroying particularly your liver by gaining more and more weight just in your liver, but putting on the fat, so it's no longer a functional organ.
It makes me physically uncomfortable to hear you talk about it.
Yes, well, these are scary things, and I was just looking at the obesity rates in the United States, and I kept having a problem with the numbers because it kept saying a third of people are overweight, and then I'd look at another number, and I suddenly realized that they were separating out overweight and obese. Overweight is a third. Obese is 40%.
Really?
Yes.
So the combined number
as
of
far
people
as I can
who
tell,
are overweight or
is 70
obese?
freaking percent.
Wait, so I'm sorry, where does overweight start?
BMI of 25.
All right.
So I technically am overweight.
But that doesn't make any sense.
Well, I exercise. I have muscle is denser than fat. That's why fat floats on water and muscle does not. Fat is less dense. And so if you just look at it sort of average muscle density and, average muscles, 25 is overweight. And it's also culturally dependent. So BMI is relatively an arbitrary, not, as you say, making sense number, but it's something that you can use over a large population. But for individuals, it doesn't make much sense. So, for example, in Indonesia, overweight BMI is 23. I don't know if I've been 23 my entire life. I would have counted it as an overweight Indonesian at any point in my life. So these things are culturally determined, and as we know,
well, as health is too, and the diet is culturally determined. The way your body reacts to the diet is culturally determined.
We're not genetically different enough for there to be, in my opinion, standards that should be that different between cultures. That is something where we're just arbitrarily deciding we like it that way. And but on
the average, if I go walking down the street in Indonesia, most of the people that I see are way skinnier than the people that I see here. And I don't know if that's a preference or the way that they are and the food that they eat.
They measured their average healthy population and said, oh yeah, BMI 23. We measured our average healthy population and came up BMI 25. But it was entirely arbitrary.
We're all humans. It probably should be lower than 25. Okay.
But what would happen if we did this again and looked at healthy people and started off with a new average? We might be at a 28 BMI is overweight now, but the 25 is useful, even though I don't like it for myself. I think mine's probably more like a 26 and I don't feel overweight. It's useful because you can put it into a model. If your weight is going up when the doctor is looking at, year on year, you have a BMI of 25 or above, and you have high cholesterol, they can put that into a model. And my doctor told me I had a 10% chance of dying in the next 10 years. I don't think he's right, but on average, someone with my numbers would.
And this is where my doctor would tell me that personal risk is not the same as a population level relative risk.
Exactly. So BMI only really makes sense for population levels.
But nonetheless, personal risk is still there.
Absolutely.
And the medications that he then recommended in the next sentence to you actually make a difference on the personal level.
Exactly. So he then recommended things that would control the cholesterol.
Yes.
And so I knew that the BMI didn't matter, but that having a high cholesterol might be something I would want to address anyway, regardless of what my BMI was, because there's many, many correlations of cholesterol with clogged arteries, and I don't want that.
Mm-hmm.
And this is something that happens to basically all of us as we get older.
Mm-hmm.
But there's all sorts of variation with, BMI and cholesterol and blood pressure, et cetera. Normally, as your artery gets clogged, you need to put more blood through that artery, so your blood pressure goes up.
Mm-hmm.
So I have high cholesterol, but my blood pressure is fine. So I don't think that I'm actually in that situation yet.
Mm-hmm.
Certainly, that would have gone into the equation. If my blood pressure was higher, it would have been, much, much worse. So anyway, there's direct relationships between all of these metabolic issues, from blood pressure to circulating triglycerides. All of these things are directly related to sugar. As you eat sugar, it is the top priority for your body to control. One, keeping blood sugar high enough to keep your brain alive, but keeping it low enough because sugar itself is dangerous. Sugar itself is a poison. And if the sugar goes too high, the sugar itself will start poisoning you and can poison your brain. So it needs to be kept within a very tight range. And so our body's always working to keep it within that range. So if you're eating something, let's say a bag of potato chips, you then have to start thinking about what else is in that food, and what they talk about as the glycemic index and the glycemic load.
Mm-hmm.
Potato chips are particularly insidious. They are pre-cooked, they are thin, and so even though there's some cell membranes with maybe a little bit of cellulose in there, they're mostly pure starch, and the potato starch is actually one long string of glucose. When you eat that, you have so many enzymes that release that glucose that your blood glucose will go up faster than if you just eaten a spoon of sucrose. Sucrose is a disaccharide. It is made up of glucose and fructose together. So when you eat a spoonful of sucrose, you have to break that into two different pieces, and then you can digest the glucose. The fructose will keep circulating for a while. We'll talk about that in a moment. So you actually get sugar out of potato chips faster than you do out of literally just a spoon of sugar.
So a potato chip is essentially a bomb.
Yeah, so you're looking at a bowl of sugar when you look at a bowl of potato chips.
It just goes in your body and
now,
goes, boom.
Yeah, and I love potato chips, but I've been programmed to, because my brain gets a really nice response from those potato chips. Mm-hmm. It gets that blood sugar spike very quickly, gives me a nice release of dopamine, and said, you did good. You got, whatever you did, keep doing it. Keep eating them, don't stop. Just keep piling those in there, because you are getting calories so fast. But what else is happening when the blood sugar goes up? So I'm getting a huge spike of blood sugar. That's your glycemic index, how quickly that blood sugar goes up. That's giving you more of a dopamine response. You get more of the addiction relationship, and it's going to tend to cause a peak and crash situation. But there's also the glycemic load. That's how long how much actual sugar there is total. So how long it's going to circulate within you. And so potato chips are going to have a very high glycemic load because it's almost all glucose. Juxtapose it with something, say, watermelon. Watermelon would have a very high glycemic index. It's sweet, boom, you get a quick sugar high, but it's only seconds long because there's very little actual sugar in watermelon. You could eat an entire watermelon and it would eat like 2 potato chips.
You eat a whole piece of watermelon very quickly.
Yeah, and it's
you get all the sugar all at once, and then it's just gone.
And it's just gone. And it would be like eating a nibble of potato chip. And your body would never let you do that. You can't eat just one. Those addictive behaviors just kick in very, very quickly because of that dopamine spike. So anyway, when you get this insulin spike and then that you keep on getting more and more sugar in you, your insulin remains high for a while. And you're trying to lower that blood sugar, but you keep putting more in because you've got a whole bunch of potato chips in your stomach. When this is happening, you also have all the other things from the potato chips, particularly the triglycerides. So you now have a whole bunch of fat in your body. This fat cannot be removed from your body until your body's taken care of the glucose. And so the triglycerides keep going round and round and round and clogging things. When blood sugar is high...
So you're saying that the triglycerides literally circulate through the bloodstream and get caught on things in the bloodstream and clog things up physically.
Physically, yes, yes. And so we tend to think of this as cholesterol, but cholesterol is actually something that's made to move fat around. And so good cholesterol takes fat out of your blood system and takes it to your liver to be processed. But if insulin is high, your body doesn't want to do that. Your liver is busy. Anything that goes to your liver is going to cause even more of a problem. So your body says, don't take fat out of your to your liver. Take fat from your liver. Get as much away from your liver as possible so that your liver can handle all the glucose. So you end up with, as your insulin goes up, you actually increase your triglycerides, let alone what's coming from the potato chips. Even if there was no fat in the potato chips.
You're actually increasing your triglycerides internally.
Internally, even without eating fat. Just the sugar is going to increase the fat flowing around your body.
So your bloodstream is being flooded with triglycerides.
And increasing the bad cholesterol, because the bad cholesterol is removing fat from your liver and taking it to your body. And that bad cholesterol, a low density lipoprotein, is structurally a lower density protein, lipoprotein. So lipo is the fat side. Protein is the molecule that gives it information.
Low density, you mean it's literally like spread out like
puffier.
A snowflake.
It's spread out like a snowflake, exactly. So the lipo part, the fat, sticks onto your triglycerides. So fats stick on fats. So it's like
literally like it physically pokes in and adheres.
Sticks to it. Yeah. So the fatty part sticks to the fats. And then the protein tells it where to go. But the low density ones are big and puffy. And now they're stuck onto a big triglyceride. And as they move around, they run into things just with turbulence in your blood system, and they end up sticking stuff to the walls of your arteries.
Where they're not supposed to have
Where
gone.
they're not supposed to have gone. And they're sitting there stuck to it, and they've got big prongs of protein sticking out of them.
But in this case, this happens because the liver is not accepting them.
It's not accepting it because
they're going round and round.
Right.
In a normal situation, when there wasn't glucose being dealt with, they would be accepted into the liver. They wouldn't spend as much time, so there would be a lower likelihood of them getting caught in places they should not get caught.
If you had just eaten a bowl of broccoli instead of potato chips, okay, you would have some carbohydrates, which would then be turned somewhat into glucose. You would have a tiny response of insulin, very low fat in there. So you
literally need to work harder to convert what's in there.
Right. So you would very quickly. First, you would get rid of the sugar that's in the plant matter, in the carbohydrates, and you would absorb that as quickly as possible. Any fats would take longer to digest. So by the time the fats got into you, you pretty much would have dealt with all of that sugar. Those fats would be taken quickly to your liver by the good cholesterol. Your good cholesterol would go up because it would be removing any fats it found because it wants to store those. It would grab those in your blood system and take those to your liver. And so it's how quickly the sugar gets into you and the size of the spike and then how long it circulates that cause all of the other problems.
The glycemic index is how quickly the sugar gets into you. The glycemic load is how much you're putting in over time.
In total. And so both of those things are bad, and they're both bad on their own, but they're really bad together. And potato chips are the worst together. They're really bad on their own, but any sugar combined with fat makes the fat much, much worse.
So I distinctly remember in the years that we were working out regularly and we would go do kung fu and then we would go have a steak and a potato, and you're like, this is the worst thing we can do to ourselves.
Yeah, absolutely.
Because you're saying because of the starch of the potato, which is immediately accessible as glucose, and then the fat of the meat, which does exactly what you're talking about, raising our triglycerides.
Yeah, there's some real dark magic when it comes to insulin and exercise, though. There are weightlifters who will specifically fast and then eat a starchy meal to increase their insulin.
Just before.
And then work out. It doesn't just give you energy for the working out. That insulin is an anabolic steroid. You will increase muscle mass, but with fat preferentially. And so this is how sumo wrestlers get so huge, is they're specifically basically hacking their own body's response to increasing an insulin spike to cause anabolic steroids to be produced.
That's amazing.
Yeah, and it does work, but it will preferentially go towards fat, as well as building...
There's a cost.
There's a cost, yeah, exactly. There's a cost. But it will build muscle as well. And so, if you work out enough, you can kind of balance things.
I would not want to go up against a sumo wrestler.
No, exactly. They're real. That's not a fake thing. Yeah, exactly. And they're huge. Yes. And they've done this by adjusting their own anabolic steroids internally.
That's phenomenal.
By working with the insulin. And it'll happen even faster if you're sleeping. So if you've gotten an insulin spike and you go to sleep, you will preferentially turn that into visceral fat. And so you'll get fatter faster while you're sleeping than if you're exercising, because obviously you'll be burning some of it.
Well, this speaks more and more to metformin, that drug that.
Yeah, well, indeed, that keeping insulin low is a good way of not building fat
and removing visceral fat and
we were talking about the metformin also increases the oxidative metabolism of fat in the liver, so it increases the rate at which fat is processed in the liver. And so it slows down the progression of fatty liver disease. Now, if you already had type 2 diabetes, I would wonder about, okay, so type 2 diabetes would definitely be treatable with metformin, but if you had a swollen liver due to fatty liver disease, I don't know what would happen next.
Well, I don't know that they'd be recommending it.
I don't think they would, right? Because it would be very difficult to process fat that way in your liver if you already had a damaged liver.
Yeah.
But it probably would improve liver health overall.
But this is fascinating because this is literally this is body hacking, and this one is metformin sounds like a relatively gentle body hack compared to what you were saying about Ozempic.
I looked at the numbers for metformin, and it seems as though if anything, it's better than the placebos in terms of out of 100,000 people. More people will have the side effects that they sometimes attribute to metformin who didn't take the metformin than who did.
Makes sense.
So anyway, the Ozempic is much more dangerous. Ozempic seems crazy to me.
It's much more popular.
For
off-label use.
It binds directly to the glucagon-like peptide receptor. So again, glucagon is the thing that actually is releasing blood sugar from the liver, and if you block that, I guess you're controlling your blood sugar and increasing your insulin in some way that helps you. They were not actually predicting that Ozempic was going to do anything beneficial. It was a sort of happy accident. You would not predict it by looking at the receptor sites that it would have these effects. But among its many effects are slowing down of gastric emptying. So when you eat food, you fill up your stomach. It's sort of like a composting system where composting is most efficient if you do it all at once, and then you let it break down, and then you take it out and you start the next batch. However, you can do it a little bit at a time. Just keep adding food into the composter. And it'll be mostly digested when it's done, but it'll be a little bit less efficient that way. So we tend to be most efficient with our meals by eating a big meal and then waiting. But you can also just eat little meals all the time. If you do that, you're going to tend to feel kind of full and bloated all the time because your stomach can't quite get rid of the food as quickly because you have big chunks in it. Mm-hmm. And so that is gastric emptying. If you just literally keep putting food on top of food, eventually you'll get ill and start throwing up because there's nowhere to put the food. If people have damaged stomachs, they can only process food so quickly, and so they have to eat very small meals, infrequently to allow the stomach to basically do gastric emptying. If you're taking Ozempic, you have very low gastric emptying. You don't empty your stomach.
It just doesn't sound good.
So it just sits there and you're full all the time. And so the side effect this has is it causes you to throw up and it causes you to have diarrhea. I think most people are aware of this.
Is this? I mean, does everyone get these side effects, or is this one of these things that like a small number of people have these?
I can't quite tell. It seems like a very large number of people have at least the nausea and consider it to be not a side effect, but the effect. Because they're not hungry. That's the whole point. They feel full. They feel nauseous. They're going to the bathroom all the time, but they're losing weight.
I don't like it.
And yeah, they're getting rid of the fat. So yeah, the metformin I think is much healthier for you in some ways. Again, not that kind of doctor, just to remind everyone. I'm not recommending things as a medical doctor, but I'm just talking about how they work metabolically.
It sounds completely different.
They work completely different methods. They're targeting different targets. What I really like about what you're talking about with the metformin was that it actually increases your oxidative metabolism. So it's burning through things much more quickly.
Well, it also sounds like it works. It would work very well with intermittent fasting. That a couple of hours of ketosis combined with the effects of metformin would kind of be multiplicative of the beneficial.
Yeah, I don't.
effects.
Depending on how long you do the fasting, you shouldn't be going into a real acidosis.
No.
You should be, but you definitely should initiate fat burning.
Right.
That's the whole point.
Like an initial
Right.
ketosis for 1 to 4 hours a day.
I don't even know if it would technically be testable as true ketosis.
Oh, really?
Well, true ketosis means you're starting to actually produce ketones in the urine that would be measurable coming through, your kidneys. Right. I don't think it lasts long enough for either a real change in pH in your blood or a increase in ketones in the urine.
But it is attacking body fat.
It's doing that, right? It's starting the same. It's starting the same metabolic process that would lead to ketosis. It's run through your glycogen reserves,
right? And
it's starting to burn fat. When you start to burn fat, you have different metabolic byproducts,
right?
Some of which are ketones.
Right, there you go. Right, and if the metformin helps in reducing the fat in the liver, then when you
would burn it faster.
You go faster towards.
Yeah, it would increase the rate of fat burn in the liver.
Which is in this case, it's not. It's a beneficial thing. It's fascinating. It's a fascinating body hack.
Yeah, and I really am interested in the way glucose is related to our overall sort of evolutionary desire to become as fat as possible, and that we've really evolved into creatures that absorb it and hold it better than most others.
But in our mid-50s,
we don't have an easy way of getting rid of it.
This is not where we want to be.
It's not where we want to be, and as a nation, we are ridiculously overweight.
It's kind of hard to believe.
It's really kind of hard.
The numbers you said were.
I had to look them up 3 times because.
But again, the way they're grading this I don't know that overweight is necessarily overweight. Is there an actual reduction in life expectancy at what they're calling overweight?
On average, yes, but not for an individual. So on average, yes, because overweight usually means fat. But in some people, it could mean muscle or,
right,
may or may not be good, depending.
Right. We need a better way of reckoning this so we can get better information out of it for individuals.
Native Alaskan populations that eat almost only meat because there's no vegetables. They get their vitamin C from whale blubber that has been uncooked and literally tastes sour. It's got so much vitamin C in it. Like a narwhal or a beluga. They have relatively high body fat, very high BMI, and their blood pressure is fine. Their triglycerides are fine because they have tremendous amounts of exercise. So exercise is absolutely part of the equation. You can keep your blood pressure way down by increasing the blood volume through your heart on a regular basis, which you do through exercise. Mm-hmm. So many of these problems, the two sides of it are glucose and exercise. Exercise burning the glucose. I wanted to talk one more aspect of glucose, why it's so strange, is its relationship to stress. So
yes,
and so this is one of the reasons why I had to stop studying it in my shrimp, because it was too weird for them. In a crayfish or another crustacean, if you leave them out of the water, they're clearly upset and stressed. What starts happening is they start flooding their hemolymph, the equivalent of their blood, with glucose. And you can measure how stressed they are by the content of glucose in their blood. And it's considered a 1-to-1 relationship. If they're stressed, higher glucose. I think evolutionarily, we have done this to ourselves as well. We've made it a two-step process.
So are you saying you can make shrimp more delicious by stressing them out before you cook them?
Possibly. I'm not sure if you could actually taste the difference. We're talking about micrograms.
Sounded like something that chefs could use. Anyway,
it's microgram difference, but yeah, it's measurable and it's real. So I think stress is sugar. I think sugar is stress and stress is sugar. And so that high sugar levels are stressful on the body. Stress causes high sugar levels. So when we talk about corticosteroids, those are actually glucocorticosteroids. They're derived from glucose molecules with the steroid part of it sort of on the side. This is to signal, in my opinion, the ancient stress pathways related to blood sugar. What does a glucocorticosteroid do? It causes your blood sugar to go up. It fights against insulin. If you're stressed all the time, it's another pathway to type 2 diabetes. You become less sensitive to insulin. It causes your blood sugar to go up. It's going to cause all of these other things that are bad for you to happen that are related to high blood sugar. So you combine stress with all the other effects of sugar, and you have a real 1-2 punch there, and you can go directly into type 2 diabetes very, very quickly. So I think that it's not just that blood sugar going up is a response to stress, but in some ways your body is measuring your stress by your blood sugar. And so it is stress.
Well, like you said, that too much stress is because, I'm sorry, like you said, too much sugar in the bloodstream becomes very quickly dangerous. We have a very narrow band that we have to exist within. So
yeah, it's literally physical stress.
We're monitoring this all the time.
Yeah. So it is stress itself. And so, under normal conditions, you see a saber-toothed tiger, you want your blood sugar up there so you can get pumping into your muscles right away. You don't want to be, have insulin taking any and putting it into your liver. But in our day-to-day stress, now we're failing to store the blood sugar. It just keeps going round and round again. And then one last thing I want to mention is sodas. So the high fructose corn syrup that we're drinking in our sodas. Normally you would say, oh, fructose, that's good for you. It's in fruit. It's got it right there in the name. And it's somewhat true. You can't digest fructose as quickly as you can digest glucose. Therefore, the glycemic index of fructose is slightly lower. Slightly lower. You don't get quite as fast a spike because you can't digest it as quickly. First, you have to metabolize it into glucose in the liver, and then you can take that glucose and store it as glycogen. But what happens when you have high circulating fructose? You can't get rid of that fructose, and so you are sitting there with the high triglycerides and the bad cholesterol again. And so it's just going round and round until you've gotten rid of all your glucose. You're slowly turning it into glucose, and it just keeps going round and round as you slowly metabolize it in the liver. Your liver is now going to be overwhelmed by the sugars you're encountering and start turning some into fat. Now you have less of a working liver because you've turned it into fat in your liver, so you don't have don't have liver cells to process this sugar. So the more sodas you drink, the more it's going to end up with high fructose circulating. You end up with overall high blood sugar, and you're going to end up with high triglycerides and the bad cholesterol just from drinking sodas. Zero cholesterol in the soda, zero fat in the soda, but it's all being basically signaling your body to increase your fat and cholesterol. So I wanted to end up with that happy note there.
So I have a question, and I don't know if you're prepared to answer this, but
soda and fries would be the worst.
So I have read in the past, and I haven't been thinking about this for a while, but you're making me never look at a milkshake the same way ever again and think that I need to run from all sugar. But the question is, these sodas that have no sugar in them, but they have sweeteners. I have read that sweeteners can still cause these responses even if they're not sugar.
Okay, some of the responses, not others. They're not going to be nearly as bad for you in terms of overall metabolizing the liver, etc. But they will feed your dopamine addictions, because you'll still get the dopamine response to the taste, the sweet taste. And there will be some metabolic changes because anytime you eat any food, your body responds to the food before you can digest it. I drink coffee. I'm going to get more energy before that caffeine is actually giving me the energy. So we're always a little bit in front of whatever we put in our bodies.
Mm-hmm.
And so that sweetener is going to act a little bit like the sugar until your body figures out it's sugar.
Will it cause a glycemic spike
No,
in any
not-
way?
not in
Will
the
it
same
cause
way.
an insulin spike because the body thinks sweetness is coming?
For a moment, there might be a brief moment, but generally, most of the studies that are done on sugar compare it to these sweeteners. So that's the placebo group is an artificial sweetener.
Oh, it's not nothing. It's an artificial.
So you
sweetener.
can't tell the difference.
Right,
Otherwise,
right,
it's
right,
not
right,
a placebo.
Right.
I could actually tell the difference usually.
Fascinating.
Yeah.
So, I mean, I guess overall, lowering the amount of sugar taken in is recommended, but specifically lowering. Overall, lowering the amount of sugar taken in is called for, but additionally, being like if you sit down after a meal that you've had a very, very good meal and had a healthy meal, but then you have a sugary dessert, you're saying that your body at that point stops digesting everything and only takes care of the sugar that you
Correct.
just put into you.
Correct. And this is why we love dessert, because it helps us feel full. The insulin tells you to stop eating, and the feeling of fullness in the belly goes along with that really well. I didn't actually end up talking about the hunger hormone ghrelin or the satisfied hormone leptin, but
Well, let's talk about that.
yeah. They're somewhat related, but these are the things that tell you when to eat and when to stop eating. Ghrelin is directly related to insulin, but they're working at different time scales. Leptin is actually made by fat in your body, so you should be less hungry the more leptin is being produced.
Mm-hmm.
But the problem is once a fat cell has been made, it stops producing leptin, and so your leptin levels go down, and so you become hungry. Leptin tells you to stop being hungry, and fat produces it. But as soon as you stop feeding your fat cells, they just make more leptin. So once you've achieved a fat cell in your body wants to never let go of it, and you'll be hungrier because you now possess that fat cell.
Oh, God.
I know, we're evil to ourselves.
Evolution really has conspired to work against us in the modern era. It's amazing.
Yeah.
Fascinating, Josh. Thank you so much. Until next time.
Until next time.